So in this example, we want to find the inverse Laplace transform of s to minus a, where a is not an integer and it lies between 0 and 1. So that means we've got a branch cut and a branch point. So a branch cut with a branch point at the origin. So we choose the branch cut to lie along the negative real axis. So the contour is going to look like this. This is our C. So this only has a singularity at the origin. It's not a pole because A is not a integer, it's just a singularity and also a branch point. So we need to be careful to check that the integral around here, whether it's 0 or not. But there's no residues to work out. So this is R, this is minus R, this is minus R. And we're calling this distance is delta and this radius is epsilon. And we're saying delta is much less than epsilon and epsilon is very small. Okay, so we take the limit as r goes to infinity, epsilon goes to 0 and delta goes to 0, or the contour integral of e to the st times s minus a ds. So that's going to give us 2 pi I times the thing we want. So let's just write f bar s is the Laplace transform of the thing we want. Right, so that's this integral up here. We can say that this integral, this integral, this integral, this integral all go to 0 just because f bar s goes to 0 as s goes to infinity. So that just leaves us with the integral along here, the integral along here, and the integral around here. So we've got the integral along here is from infinity to 0. It's s equals r e to the I pi here, and s equals r e to the minus I pi here. ds equals minus dr, so I get a minus sign. I'll use, okay, I'll use the minus sign there, and we've got e to the minus rt times, so s is r e to the I pi, so I get r to the a minus a, and e to the minus I pi a, just substituting s equals r times e to the I pi into here, dr. Then I've got the integral back, so again I'm going to have a minus from the ds. Then the difference here is I've got e to the minus I pi. When I raise that to the minus a, I get a plus, so it's e to the I pi a dr. So the two integrals don't cancel out because of this differing. And then I've got the integral from pi to minus pi, limit as epsilon goes to 0 of this thing. So it's e to the, okay, well, we already know that this thing's going to, I'm not going to write that each time. So it's going to be so yeah, s is equal to e to the I theta. So I've got epsilon to the a minus a, and I've got times e to the I theta to the minus a, and the ds turns into epsilon e to the I theta times I d theta. Okay. So this thing I'm not going to write. This is just going to be e to the epsilon, which is tending to 0. So that just gives me 1. Okay, so the important thing is to work out what's happening here. So I've got epsilon to the power 1 minus a. So this is of order epsilon to the 1 minus a, which is going to tend to 0 as epsilon goes to 0, because a is between 0 and 1. So we're okay with that. So all that's left are these two integrals here. So I can combine them. I can take out this factor, these factors here, and I've got 2 pi I. Okay, well there's no residues here, so basically this is equal to 0. I can now write, if I divide both sides by 2 pi I, move these things onto the other side, I can now write that f of t is equal to 1 over 2 pi I. Then I'm moving this onto this side, and I end up with e to the I pi a times, and then I'll get, if I use this to make a plus and swap the limits, it's the same integral, but instead I've got this, so it's basically this multiplied by this integral. So this looks familiar. This is simply sine pi a divided by pi. So rewriting things. Now, for this, you need to know about the gamma function. So I'll just write down the definition of the gamma function. So gamma of, doesn't matter what you use, okay, I'll call it p. Gamma of p is equal to integral from 0 to infinity of e to the minus, just some integration variable, e to the minus u, times u to the p minus 1 of, and then du. And we just need that the real part of p needs to be greater than 0. So we see that if we make this substitution, u equals rt, then we get it into the form of the gamma function. So let's make that substitution. So we get 0 to infinity e to the minus u. So that means r is equal to u over t. So we've got t to the, okay, let's just e to the minus a, and t to the minus, divided by t to the minus a, which is the same as t to the a. So I can put this t to the a out front, and then dr is du divided by t. So dividing by t, I get t to the power a minus 1 up front. Okay. So comparing with this, I've got p minus 1 is equal to minus a, so therefore p is equal to 1 minus a. So this is just equal to t, so the a minus 1 times sine times gamma of the gamma function of 1 minus a. Now we can actually do a little bit more with this, because there's an interesting property of the gamma function. Which is that gamma a times gamma 1 minus a is equal to pi over sine pi a for any a. So that any a apart from when a equals 0. So we can see that therefore gamma 1 minus a times sine pi a divided by pi is actually, all of this is just equal to, moving this down here, is just equal to 1 over gamma a. So the final answer is t to the a minus 1 divided by gamma of a.